All right, let's talk about titration. So before we jump into titration, we need to quickly talk about molarity and stoichiometry again. So molarity and stoichiometry is our relationship between volume, moles, and molarity. Remember, moles times volume is molarity, volume times molarity is moles, and moles divided by molarity is volume. So given any two, you can find the third one. So when we're doing stoichiometry with involving molarity, involving a concentration, generally we're going to start with a concentration or volume, convert that to moles, moles to moles, and then convert that to concentration or volume. So it's a modified version of our grams to moles to moles to grams, right? So if, for instance, we start with the volume of A, multiplied by the molarity of A to get moles of A to moles of B by the stoichiometric ratio, that's always the same, and then dividing the moles of B by the molarity of B, you can get the volume of B. Or if you had the volume of B and you needed the molarity, you take moles divided by volume, and that'd give you molarity. So this comes into play in titration. So titrations is basically adding a volume of a known titrant into a solution of an unknown concentration. So this is the equipment that is used for this. So this is called a burette, and it's like a graduated cylinder with a nozzle. The stuff in the burette is called a titrant, and the stuff in the flask that's underneath would be an unknown, and generally you're adding an indicator. Now, an indicator is used to tell you, to have a visual indicator as to when the reaction is done. So this is typically done with acids and bases, and what an indicator shows is the endpoint. Now, the endpoint is not the same thing as the equivalence point. So the equivalence point is where the reaction is 100% done. The endpoint is where the indicator will change color. For an acid base, usually this is based on pH. So what you have to do is you have to find an indicator that will have an endpoint that's close to your equivalent point. So when you hit your endpoint, you basically hit your equivalence point. And so in the lab, a lot of times you'll use something like phenolphthalein. Let me write that out for you. So it's pheno, PHTHALEIN, phenolphthalein, and it is in pH less than 7. It is clear, or colorless, is the better way to put it. And in a pH greater than 7, it is bright pink. Okay? So if we're doing a neutralization between an acid and a base, well, our equivalence point, when we have equal amounts of acid and base, should be pH 7, right? So what we do is we would put phenolphthalein in our acid and then titrate with base. So typically you'll put your unknown acid here, and then you put, like, usually it's sodium hydroxide there, and you'll titrate it, and then once it turns pink, then you're like, okay, I'm done. And then what you can do is you can measure the volume, right? So the titrant is usually standardized. What that means is you basically run an experiment with a known amount of acid to get a really, really, really precise measurement on the molarity of your titrant, because you're doing very small drops. So, the difference between 0.9931 and 0.9814 could be a big difference, right? You would round those both to 1, right? Actually, let me add another 0 because usually using 0.0, right? You'd round both of those to 0.1. But this is a sensitive enough technique that could actually make a difference. So you standardize the titrant to get a really precise, like, oh, it's this and this, but not, more precise than 0.1. You're giving yourself more sig figs to work with. So usually you'll start with that. And then what you do is you take the volume of titrant, calculate the moles of titrant, which gives you the moles of unknown, which lets you calculate the mass or molarity of the unknown. So I know my milliliters of titrant because that's how much I added. And then I can use since I know the molarity of the titrant, I can find the moles of the titrant, right? So you multiply by the molarity of the titrant, okay? And then this is from the chemical equation, right? Stoichiometric coefficients. And then the unknown, right? You can either find the molarity or you could find the grams, depending on what's going on. So let's look at a couple examples. So how many milliliters of 0.1 molar sodium hydroxide are needed to neutralize 30 milliliters of 0.46 molar hydrochloric acid? Well, here's our balanced chemical equation. We say, okay, I've got 0.03 liters of hydrochloric acid. And there's my molarity is 0.46 moles per 1 liter. So liters cancel. And then here's my stoichiometric coefficient. It's 1 to 1. 1 mole of sodium hydroxide for every 1 mole of hydrochloric acid. So that's cancel. And then I've got 1 liter for every 0.1 moles of sodium hydroxide. So that's my 0.1 molar. I flip that ratio. So moles of sodium hydroxide cancel, and you'll get liters of sodium hydroxide. So I get 0.138 liters, which is 138 milliliters of sodium hydroxide. Okay, let's look at another example. If it takes 25 milliliters of a 0.25 molar solution of sulfuric acid to neutralize a solution of aluminum hydroxide, what is the mass of aluminum hydroxide present in solution? Okay, so here's my balanced chemical equation, and I'm starting with 25 milliliters, so 0.025 liters of sulfuric acid. I want to convert that to moles, so I'm going to multiply by the molarity. And then I want to convert that from moles of sulfuric acid to moles of aluminum hydroxide. So the ratio is 2 to 3. So moles of sulfuric acid cancel. And then I'm going to multiply that by the molar mass of aluminum hydroxide, which is 78. So moles of aluminum hydroxide will cancel. So now I'll get grams of aluminum oxide, which turns out to be 0.325 grams. If it takes 45 milliliters of a 0.3 molar solution of sodium hydroxide to neutralize 90 milliliters of hydrochloric acid, what is the molarity of the hydrochloric acid solution? So now we're looking for molarity. So we've looked for volume, we've looked for molarity, or for grams, now we're looking for molarity. So we're starting with, so back to this equation, we're starting with 0.045 liters of sodium hydroxide. Again, multiplying it by the molarity to get moles. Then multiplying that by the stoichiometric ratio to get the moles of acid. So we got 0.0135 moles of acid. We're going to divide that by the volume of acid in liters, and that'll give us the molarity. All right, let's do some practice. What volume in milliliters of 0.2 molar sodium hydroxide is needed to neutralize 39 milliliters of 0.73 molar hydrochloric acid? Okay, so we'll start with 0.73, or sorry, with 0.039 liters. Okay, and then is 0.73 moles of HCl per 1 liter. Okay, liters cancels. Then we're going to multiply that by the ratio, which is 1 to 1. I've run out of room, so I'm just going to continue on the next line. So just coming down here. And then we're going to multiply that by 1 liter per 0.2 moles. Okay, so liters of hydrochloric acid is canceled, moles of hydrochloric acid cancels, moles of sodium hydroxide cancels, and you get 0.142 liters of sodium hydroxide. If we convert that to milliliters, we get 142. All right. If 145 milliliters of 0.2 molar sulfuric acid is needed to neutralize a solution of lithium hydroxide, what is the mass of lithium hydroxide in solution? So here, since it's not 1 to 1, we're just going to need to write this out. H2SO4 plus 2 LiOH gives me Li2SO4 plus 2 waters. Okay, so the ratio is 2 lithium hydroxides to 1 sulfuric acid. Okay. So I've got 0.145 liters of H2SO4, and I've got 0.2 moles of H2SO4 per 1 liter of H2SO4. Okay, now I've got 2 lithium hydroxides per 1 H2SO4, and then I'm going to multiply that by the molar mass of lithium hydroxide, which is 7 plus 16 is 23, plus 1 is 24, so 24 grams per 1 mole. Okay, so that cancels, and that cancels. So punch it into my calculator. And you get 1.392 grams. Ignore this number. Finally, if 73 milliliters of 0.1 molar sodium hydroxide is needed to neutralize 153 milliliters of phosphoric acid, what is the molarity of the phosphoric acid solution? All right. So, we're starting with 0.073 liters, 0.1 moles of sodium hydroxide per 1 liter. Now here again, so we've got H3PO4 plus 3 NaOH gives me Na3PO4 plus 3 waters. Okay, so 1 H3PO4 per 3 NaOH, and that's going to give me, so liters cancels, moles of sodium hydroxide cancels, so I've got 0.00243 moles of H3PO4. I'm going to divide that by the liters, which is 0.153. And you get 0.016 molar phosphoric acid.